How do I remove it?
Just click OK and yes, and
This one.
yeah, you just show it.
Okay. Okay.
Perfect. All right, everyone. Want to get started? All right. So today we're happy to have Ilya Essen presenting for us. Ilya did his master's at Weizmann working on weak measurements. He then moved for his PhD to Technion to work with Antonella Lindner on driven systems and stochastic systems. His next stop was a postdoc at Caltech, where he worked with Gilbert Bell, also on equilibrium physics and driven systems. His next stop, which is going to start apparently in a couple of months, is a faculty position at Bar-Ilan University. And today he's going to tell us about heating in slowly driven topological systems.
Thanks, Jean-Louis, for this nice introduction, and also thanks for inviting me here. By the way, do I need the mic, or I think I can hear myself on the so I think it's working. Okay back there? Yeah. Okay. Oh, but it should be from the mic in my computer, so.
Can you hear him?
Okay, good. Yeah, so I'm enjoying a lot visiting Ithaca and Cornell. It's a very beautiful place, even though it's a bit cold. But yeah, it's amazing, and thanks, Eric, for taking me, to see it on. Yeah, so today I will tell you about the problem of heating in driven adiabatically driven topological systems. And the so the adiabatic systems are known for their diverse applications. For example, in transport, if you drive a quantum wire slowly, we can induce a quantized current in this wire, and that has various applications in electronics and metrology. In computation, we have the idea of adiabatic state preparation and topological computation. So the first idea helps to solve hard mathematical problems and prepare entangled states. And the second, the topological computation, proposes to use anyonic grading to realize quantum gates. And there is another recently proposed adiabatic system, which I would like to mention. And this idea realizes two drive setups to create a nonlinear converter of frequencies, which can have quantized conversion rate. And in many of these adiabatic systems, they require infinitely slow drives and non-interrupting setups. And of course, these conditions is very hard to realize in actual experiments. And if these conditions are not met, then the system starts to absorb energy from the drive, and eventually it heats up. And then instead of this nice, pure quantum states, we will arrive at boring infinite temperature. No features. And of course, this heating sets limitations on the realization of the systems in actual experiments. And therefore, we need to tame the beast. We need to find ways how to control heating by designing protocols that minimize the heat production or that give rise to robust steady states with some topological response. So why this problem of controlling heating is so hard? Well, heating is essentially a non-equilibrium ergodic evolution of the many-body phase function, and it gives rise to highly complicated volume law entangled states. So essentially, the volume law entanglement means that the wave function locally looks completely thermal, although globally it is pure because it arises from unitary evolution. And so, it is in order to analyze this thermalization to this complicated volume law states, usually we do exact diagonalization, which of course limits the system sizes that we can analyze. And today I will tell you about alternative approaches, how to approach to this problem of thermalization heating in many body systems. So this is the outline of my talk. So I will start by discussing the problem of Taoist pump with interactions. And I will show that this model can have steady states with robust topological response, despite the fact that they have high entropy density. So I will start by presenting the problem of the non-interacting Taoist pump in the view of Fouquet theorem. Then we'll discuss the interaction problem and how we describe this model using non-equilibrium Griggs functions and the Keldysh formalism. And then I'll present our numerical approach to this problem, where we solve where we analyze an exactly solvable problem where the electrons interact with SYK interactions. And in the second part of my talk, I will show that heating is linked to quantum geometry. I will present this on an example of the topological frequency conversion model. I will show that heating has a geometrical description, and that gives rise to the topological bound on the heating range. And by the way, if you have any questions, please stop me at any time.
So, yeah, you will be considering a closed structure, so no coupling trace on that.
No coupling. Yeah. So let me start with the first part. So here we'll discuss steady states and interacting metallic version of the Taoist pump. And before we discuss the interacting model, let us first review the non-interacting model. So here we consider the Rice-Millet version of the Taoist pump. It consists of a bipartite lattice with two sublattices, A and B. And we modulate in time the Steiner potential, the potential difference between A sublattice and B sublattices, and the dimerization, the hopping within the unit cell and between the unit cell. And essentially, at any time, this model corresponds to a state shape, which has the following spectrum. And here we consider protocols. And of course, so of course, as a function of time, these two bands will change, will vary. But here we consider protocols where the gap will be always large. And the topological phase of this model is when the Steger potential and dimerization encircle an origin as a function of time. And if we do this modulation in time infinitely slowly, such that the system is always in the instantaneous ground state of half filling, then there would be a quantized current of exactly one electron that propagates through this chain. And in order to understand this result, or to calculate this result, we need to analyze the Schrödinger equation, where the Hamiltonian is periodic in time, because we modulate the hoppings periodically. And this kind of equations can be solved using the Fouquet theorem. This is a theorem which is named after French mathematician Gaston Fouquet, who was the first to analyze this kind of differential equations. By the way, it was very hard to find his picture, probably because he wasn't as famous back in the days as he is famous now. So no one bothered to take his picture. So it took me a while to find this image. So I hope this is the correct version. Otherwise, this is just a random French guy from 19th century. Right. So the Fouquet theorem is essentially identical to Bloch theorem. But now, instead of periodicity in space, you have periodicity in time. And instead of periodicity in momentum over the first Brillouin zone, now we have periodicity in time, in energy over the frequency of travel. Now, in crystals, we can have both periodicity in time and in space. And that allows us to have new topologies of the band structure. For example, we can have this trivial topology, or the standard topology, where the bands are just periodic in the first Brillouin zone. But we can also have this non-trivial case where the bands are sort of wrapping around this momentum and quasi-energy. So this gives rise to two chiral bands. And it looks very strange, but it is completely legal if we allow for the quasi-energy to be periodic. So this point and this point are the same in this case. And this winding of the bands around this momentum and quasi-energy torus can be used to classify topological functions. Okay, so what is the connection between this Loquet bands that we found and the instantaneous spectrum? Well, it turns out that in the adiabatic regime, where we drive very, very slowly, there is a very high overlap between the wave functions in the instantaneous spectrum in one of the bands and the wave functions correspond to one of the chiral bands in the Loquet. So that means that if we initialize our system in the instantaneous ground state, that would correspond to one of the chiral bands fully occupied. And now the current in the system can be found by integrating over the group velocities of all the occupied states. And this would be quantized in the units of the crystal momentum flooding. Okay, so this is the non-interacting Taoist function. Now let's add weak interactions. And let's assume that the model was partially filled. So such that one of the chiral bands has partial occupation and the other chiral band is empty. So now the dynamics of this model can be understood on the level of collisions between quasi-particles. And here we have two types of collisions. We have the interband collision and the intraband. And it turns out that in this model, the interband collisions are exponentially suppressed compared to the intraband. And this suppression, you can understand it because if the particle, in the case that the particle has to change its chirality to hop from left chirality to right chirality, that corresponds to this transition where the particle has to overcome very large instantaneous gap. And in this case, it has to absorb many photons from the drive, and this would be high. This would be states of high order perturbation, and therefore we get this exponential suppression for the interband process. And now this scale separation between this intraband processes and interband processes gives rise to an interesting steady state system because the interband, so the particles in one of the chiralities will thermalize with the rate gamma intra, and they will reach an infinite temperature state. However, the other chirality would remain empty for a very long time because this is controlled by the interband. And interestingly, this quasi-steady state, where the two bands are not equilibrated, will exhibit the universal current. So basically, when this band becomes infinite temperature, every single particle state has the same probability to be occupied, and therefore the current in the system would be just given by an integer times this probability for the occupation, which is the same as the density of particles. So if we divide the current by the density of particles, we should get an integer. Okay, so far, no questions. Okay, so this is the physics when we have weak interactions, but would the same physics persist when the interactions are strong, when in the case where we don't have quasi-particles? Well, in this case, it is more useful to define the problem in the language of non-equilibrium Green functions, or the Kalish formalism. And well, Kalish usually gets mixed reactions. So you either love it or hate it. That's for a good reason. So just to minimize the pain for me and for you, I will only focus on two Kalish functions, the spectral function and the lesser function. So these two functions depend on the momentum and two times, t and t prime. And by Wigner transformation, we can convert them to be functions of momentum, energy or frequency, and the center of mass time. And the spectral, so all you need to know about these two functions is that the spectral function gives rise to spectral, to the single particle density of states. And the lesser function corresponds to the average electronic occupation. Okay, and these two functions in principle can characterize the dynamics of our system. So for example, if you want to calculate the current in the pump, the current will be proportional to the expectation value of C dagger C, and this is exactly the lesser Green's function evaluated at equal times. Yes.
How is it still perturbed?
Perturbative in interaction.
Yeah.
Well, you can do it non-perturbative. For example, you can define it. What we'll do later is do it for the SYK model, the interaction. So it can be very strong.
You have a difference from that. That's what you mean by strong interaction. Like,
So the interactions will be can be much stronger than the kinetics.
with that, right?
Yeah.
Because you're going to be doing some sort of expansion. You need some small factor.
Yeah,
So
but
with the
for example with SYK you do
Yeah, yeah.
it converges.
Got it.
But it can be like with so far we didn't specify what type of interactions we include. So this is just some lesser Green's function describes
Right.
our model, but we don't specify those. Like we want to keep it. We will. Yeah.
The interacting dysfunction we don't know.
True. Yeah.
We can always write it.
Yeah. But so far I want to stay generic. So
Yeah.
we want just conceptually understand what will happen to the system. Right. So the current will be proportional to the lesser Green's function. And here we are interested in some universal properties of the current when the system reaches this quasi-steady state. And that would imply that the lesser Green's function would also have some universal properties. So for example, we know that in equilibrium, the lesser Green's function is related to the spectral function by the fluctuation dissipation theorem. And the prefactor here is the Fermi-Dirac distribution. Of course, this equation is valid in equilibrium, but we cannot assume that it is true in our strongly highly non-equilibrium problem. But maybe there would be a similar relation when the system reaches the quasi-state. And in fact, we found such a relation, but let me, before we'll tell you what this relation is, let me first review what would be the structure of the spectral function in our driven system. Okay, so here I compare, this is the non-interacting model, and here I compare the spectral function for the instantaneous model and the full Fouquet spectrum. So the spectral function for the instantaneous model can be calculated if we assume that the time in the Hamiltonian is just an external parameter and we neglect all the time derivatives. So then the spectral function just corresponds to the density of states of the instantaneous problem, and it simply describes the bands of the SSH model. Now, if we do include the time derivatives and we calculate the spectral function of the full time dependent problem, then the spectral function would actually resemble the Fouquet spectrum. So you can see that the bands get a tilt, which corresponds to the chirality of the two bands. And also there appear these side bands, which correspond to the Fouquet replica. And in fact, you can even see explicitly this winding of the bands around the torus. So if I zoom in on one of the bands, you can see that if I follow one of the lines, I end up in the value which is shifted by the frequency. And you can also see that the two bands will be separated by a large gap, and that allows us to define the Green's functions which are projected to the upper and the lower in this case. Okay, so this is the non-interacting. This is just to understand how the non-interacting spectral function will look like in our driven Taylor-Span problem. So now let's add interactions. And so here we plot the spectral function in the interacting model after the system reached the quasi-steady state. And in a second, I will tell you how we did this numerics. So what you can see here is that all the bands get broadened, and this broadening is due to the fact that quasi-particles have a finite lifetime. So here you can see that the interaction strains that we used is so large that the broadening basically is larger than the distance between the different replicas. And that means that the lifetime of the quasi-particles in this case is shorter than the period of the drive. So this is sort of plot how the lifetime of the particles will depend on the interactions, and we are somewhere here. So this dashed line is the driving frequency. Okay, so this is the spectral function. Now let's look at the lesser. And this lesser function is calculated to exactly the same quasi-steady state as the spectral function. And just from visual observation, you can see that these two functions are connected. Okay, so you can see that the lower band of the spectral function is proportional to the lower band of the lesser function, and the upper band of the spectral function is proportional to the upper band of the lesser. And of course, with two different proportionality constants. And this observation allows us to define an ansatz for the lesser Green's function, which is the analog of the fluctuation dissipation theorem, but in the quasi-steady state. So we can write that the lesser function is equal to a constant Fr times the spectral function projected to the upper band, plus another constant Fl times the spectral function projected to the lower band. And in fact, we also verified that this ansatz is a steady-state solution of the full kinetic equation up to a small, exponentially small correction. Okay, so this ansatz, in principle, characterizes fully the properties of the system in quasi-state. Yes.
So when you solve the equations, do you literally solve the Schrödinger equations like in 2 times, or you just use the distance on them and solve for this answer?
No, so numerically we solve exactly the full. I'll explain in a second, but yeah, we solve the full cardinal Bain equations to evolve in time. And this is just to have this expression, just to have some analytical understanding. But we do analytically calculate. We do plug in this equation into the full kinetic equation, and we show analytically that it is a steady-state solution after exponential small corrections. Okay. So we got this expression for the lesser Green function in the quasi-steady state. We can use it, for example, to prove that the current in the quasi-steady state will be quantized. So this is going to be like 3 lines of proof. Maybe I'll skip it unless you are interested, and then I can explain. And let me go to the numerics of the did. So in principle, it is very hard to analyze numerically thermalization dynamics of driven systems. So here we use a trick. We replaced every site on this Thouless pump by an SYK dot. So the SYK model is a very powerful tool to study matter without quasi-particles. And for a single dot or even a chain of dots can be calculated analytically exactly. In the driven case, we can still solve this model numerically on the very large system sizes. So here we use the system size of 100 sites. Okay, so every dot has n fermionic flavors where we take n to the infinite, and which can interact with all-to-all random interactions on each side. And in addition, the electrons can also hop between the dots according to the Rice-Millet time-dependent Hamiltonian, while they preserve their SYK flavor. And in order to find so we can find the Green's functions for this model, and in order to propagate the Green's functions in time, we write them as a matrix in the T and T prime direction. And then we evolve this matrix in the T direction and T prime direction, and at each step we solve the cardinal Bain equations. We assume that the initial condition was some equilibrium state of the system with quarter filling. So only these states were occupied. Okay, so this is sort of the standard procedure to propagate the Green's function in time. And then once we get the Green's function, we can extract different observables. And in particular, we calculated the current of the system as a function of time. So initially, at time t equals 0, the current was non-universal. And in fact, initially, the current will depend on how we initialize the system. However, after a few cycles, a few periods, the current thermalizes to a quantized value. And this time corresponds to the thermalization of the system, the quasi-steady state. So basically, the lower band becomes infinite temperature state. And then if you drive the system farther, the current starts decreasing, and this decay of the current corresponds to the thermalization of the system, the global infinite temperature state. So this is basically when the upper band starts getting occupied. And then, of course, eventually, if you drive the system farther, the current will decay with you. That would be the global infinite temperature state. Okay, so we also studied how the system thermalizes to this quasi-steady state. So here we define a parameter which we call distance to equilibrium, and basically measures how far is the state of the system in the projected to the lower band from the nearest thermal equilibrium state, which is parameterized by some effective temperature and chemical potential, and we minimize this distance over this parameter. So for example, if the system is in thermal equilibrium, then this distance to equilibrium will be exactly 0. And if the system is not in equilibrium, then the distance to equilibrium will be fine. So here in the left plot, we plot this distance as a function of time. And so initially it was 0, and then at time t equals 0, when we change the drive, the distance to equilibrium jumps to some high value. But then it starts decreasing, and this decrease of distance to equilibrium corresponds to thermalization of the system to the quasi-steady state. And the right figure shows the effective temperature of this quasi-steady state, and you can see that the effective temperature increases exponentially fast, goes to infinite. Okay, and then finally, we also studied how the system will thermalize to the global infinite temperature state. So basically, we analyze the population of the upper band as a function of time. So here, the yellow curve corresponds to the interacting model, and the green curve to the non-interacting model. And you can see that when we have interactions, the density of the excitations grows linearly with time. And in the non-interacting model, it stays constant. There is also this jump at t equals 0 that corresponds to the range of the system. Right, and so this is basically all the parameters that we wanted to understand in this model of driven Taoist pump. And if you have any questions about this part, this is a good time to ask.
Is there some hierarchy of energy scales between the H0 and H interaction?
Yeah, so here, right. So it is so you have sort of 3 different energy scales. You have the interaction scale, you have the gap, the H0 scale, and you also have the drive scale. So here we assume that the interactions are smaller than the gap, smaller than the H0, what we call the instantaneous gap. But they can be much larger than the previous. Yeah, and so actually you can see here that this is the current for different interaction string, and so this is the interaction string, and the gap is sort of order 1. So you can see that when the gap becomes of the order, when the interaction strings becomes of the order of the gap, the decrease. So basically, for the non-interaction case, the current is always non-universal. So the system doesn't thermalize at all. And then when you increase the interaction, the thermalization time becomes faster, but also the decay becomes faster. And if the interaction becomes stronger than the gap scale, the scale of the gap, this decrease becomes so fast that the current doesn't reach 1. It starts decreasing before it reaches the quantized value. So this is
determine if the, what was supposed to be a point that, it's not a K dot. And is the interaction translation invariant?
Yeah, the interaction with translation invariant. This is actually important for the simulation.
I see. And the hopping between the different clusters are just, I think that some points that the topological index is not changing.
Yeah,
It's not-
flavor, this way,
and it's a uniform hopping, no disorder.
no disorder. Yeah, well, actually, yeah. So the disorder would not be very important because as long as it's not of the order of the gap, it shouldn't affect the quantization of the response. And in fact, here we do include disorder. I didn't mention that, but we do include small disorder, but it's just for technical reasons. And of course, the interactions are random.
So I understood like the beginning part of like, thermalization, pure state, effective volume and all of that. And then we came to boundless pump, and that's not like a usual, it's not a Hamiltonian dynamics in the sense of like usually when we talk about, the thermalization question, you're driving the system, right? So now your metric of thermalization is steady state current. Is that what you think about thermalization? And then
Yeah, so
it looks like I've been thinking about the thermalization from the early art perspective, like pure state, with some, I don't know, circuit or dynamics, right? And it looks like maybe because I've never worked on the okay, but you're thinking about driven system, and with this 4K, the notion of thermalization is steady state, and then within that context, you're asking what attraction. Is that the picture?
So here you need interactions in order to reach the flight. So the interaction has also sort of two effects. Right? So maybe the best slide to explain this is actually here. So we start with some, our initial condition is some partially filled band over here, and this band is empty, and this would give you non-universal current. And then you need interactions for this band to thermalize, and this would be the quasi-steady state would be when this band becomes infinite temperature state, whereas this is empty. Okay, so this for that you need interactions, but then interactions also give rise to occupation of the opposite parallel band, and this is the bad. You have like a good, good effect of the interactions and bad effect. So the good effect is that they thermalize the system to the quasi-steady state.
So how are you defining thermalization? Having quasi-steady state is what you're defining.
Yeah, so I would call the system thermalized to the quasi-steady state. That's I mean, in general, thermalization would mean that the atomic entropy grows further.
But you're not talking about movement.
No, I didn't. But there's, yeah, I mean, in principle, you can also explore this, and they were explored. But yeah, but here we focus on using stuff. Yeah.
You said that there's an quantized current. It's actually the current over the cycle number ratio.
Yeah, sorry, it's this one. Yeah, I was a little bit slow. Yeah, so it's the normalized current. Yeah, more questions? Yeah.
So heat thermalization always means that you arrive at a infinite temperature state.
Yeah.
Is it possible to get some effective temperature state?
So you mean after infinite time or after some finite time? Because after some finite time, we don't get an infinite temperature state. We get these two bands which are not equilibrated. But eventually after long enough time, we get usually like if you don't have a third one, slowly. Yeah, so maybe let me continue to the next part. And in this part, so far we sort of discussed the problem of thermalization using this exact degradation, exact time evolution. And now I want to discuss the problem of heating and thermalization using a thermological approach. So this approach will give away some of the unnecessary details of the microscopic, time evolution of different particles, but in turn, it will give us some interesting insights about the connection between heating and the quantum geometry. Okay, so when we evolve the system with adiabatic drive, the wave function gains Berry phase and the Berry curvature. And the Berry curvature is, in fact, a component of a more general object, which is known as the quantum geometric tensor. So this tensor has the antisymmetric component, but it also has a symmetric component. And this symmetric component is known as the Fubini-Stokes method. So in this part of my talk, I will be interested in understanding what is the role of this symmetric component of the quantum geometric tensor in adiabatic evolution. And what we found is that this part is associated with the dissipation of energy and heat. Okay, so here we want to understand heating. So the minimal model would be some cloud of spins. So these spins are interacting with isotropic Heisenberg interactions, and all the spins are coupled to one big magnetic field. And so this is the Hamiltonian, and you can think of this model as some NMR or MRI experiment, right, where all the spins correspond to some nuclei of brains. Okay, so now let's do this experiment. So we drive the magnetic field infinitely slowly as a function of time, and all the spins will follow this magnetic field. And after one period, if this drive is infinitely slow, all the spins will come back to their exact initial position. However, if we do this experiment not infinitely slowly, then the spins will also precess around this magnetic field, and because of the interaction, this precession will be messed up. And eventually, the spins will not come back exactly to their initial position. They will be slightly deviated from that. And this state would have higher energy than the previous one. So this would correspond to heat. And if you look at the reduced density matrix of one of the spins here, so the reduced density matrix would have this thermal form where beta would be some effective temperature of the spin. And the heating in this problem would correspond to essentially to the change of beta as a function. So here we will try to understand that using the topological model. So basically, we want to write some equation of motion for the reduced density matrix of one of the spins and treat the rest of the spins as the heat bath for this one. Okay, so then we model the evolution of this density matrix using the master equation. And here in this master equation, H naught will be the coupling of the spin to the time-dependent magnetic field. And then the rest of the interaction with the spins would be included in this dissipator term. So here we assume that the effective heat bath for the spin is very large, it's Markovian, and it has flat relaxation. And in this case, this dissipator will just relax the system to the instantaneous ground state of the system, or thermal state. And then we can just parameterize this dissipator just by a single parameter tau, which is the relaxation time of the system to relax to the instantaneous ground state. Okay, so now with these approximations, well, we can actually derive this, but for the purpose of this talk, let's assume that we obtain this master equation. Now we can easily solve it. And the solution, the steady-state density matrix that solves this problem would have this form. So the density matrix would be given by the instantaneous equilibrium density matrix plus a small correction, which to the leading order in the adiabatic approximation would be linear in frequency. So now if we want to find the heating rate, or how much heat was produced in the system, we can just calculate the time derivative of the Hamiltonian with this steady state density matrix, and the heating rate should be proportional to omega squared. So that has to be such just from symmetry. So if we drive the system in the opposite direction, we still should get a positive heating rate. And if we explicitly calculate what would be the dissipation rate in the system, it gets this very nice form which has a geometric interpretation. So basically, the average heating rate in the system is proportional to this lambda, which defines a metric in some abstract space. And then the heating rate is given by the length of the trajectory on this metric, which is parameterized by the magnetic field as a function of time. And this form, this geometrical interpretation is sort of known from the field of quantum thermodynamics. And in our case, we can explicitly obtain the expression for lambda for this quantum metric, and we found that this lambda is proportional to the Fubini-Susy metric times some non-universal function, which depends on the instantaneous gap of the system and the relaxation time. Yes.
I guess I was confused. Fubini metric was in K-space.
Right. So here it is going to be in the space of the drive. So here we have two drives. So this is your parameter space.
So you said okay. So you're saying the analogous thing in the parameter space.
Yeah. Yeah. Correct. Yes.
So IJ are spatial coordinates?
So there is no space. It's just a single spin.
Yeah, it's just spinning this.
Yeah. B has B is
Yeah,
it's a vector.
B is the magnetic field on each spin, right? So GIJ is I and J are indices for different spins.
No, so you should think of one spin, which is coupled to the rest of the spins, which are heat up. So we just focus on one spin,
Yeah.
but it can be driven by some vector potential.
Oh, so
So
IJ
B is a vector.
IJ is XYZ.
Yeah.
Is it XYZ or just XY?
Okay, so it's more complicated because in the next few, okay, let me just go to the next slide and I will explicitly explain. But in principle, we have more complicated form of B here. So there will be six different components. So it will be XYZ in one magnetic field and XYZ in the other. But here it can be some generic force that drive the system. It can be any number of indices, and then G lambda, this metric would be in the space of this generalized force. Okay, and now once we got this relation between the heating rate and the Fubini-Susy metric, of course the obvious question is whether can we use this inequality that connects the Fubini-Susy metric and the Berry curvature to find bounds on the heating rate. And this relation would make more sense in topological protocols where the Berry curvature makes sense. And let's focus on one example of a protocol which has some meaningful Berry curvature. And here I want to focus on this topological frequency conversion protocol. So in this case, each spin is coupled to two magnetic fields, B1 and B2. And these two magnetic fields slowly oscillate with frequencies omega-1 and omega-2. And now the direction of the spin follows the total magnetic field, B1 plus B2. And eventually the spin will will go to around along some complicated trajectory in the Bloch sphere as a function of time. So as the spin rotates, the magnetic fields do work on the spin, but the spin can also do work on the magnetic fields. And as a result, there could be a net energy transfer from the field B1 to the field B2 with the rate, which is given by the product of omega-1 times omega-2 times some number C. And so what happens if the two drives are the two frequencies are incremental? Well, in this case, the trajectory of the spin becomes infinitely long, and eventually the spin will cover the entire Bloch sphere. And in this case, this number c becomes an integer that describes the solid angle that the spin covers. Okay, so let's focus on the incommensurate regime, and here we define a parameter n that basically parameterizes this degree of commensurability between the two frequencies. So the larger is the n, the more incommensurate is the ratio between omega-2 and omega-1, and therefore more complicated will be the trajectory that the spin does. And eventually, when we take n to be infinite, the trajectory becomes dense. And in this limit, we can in fact replace the integral, the line integral along the trajectory by the surface integral over the entire two-dimensional surface. And here we verified that indeed this is true. So as a function of n, you can see that the frequency conversion converts pretty quickly to some constant value, which corresponds to the surface integral. So now in this limit, when we can replace line integral with surface integral, the dissipation rate becomes now a surface integral over this metric lambda. And now we can try to bound it. So this metric, in this case, it's going to be a 2x2 matrix in the basis of the two magnetic fields, B1 and B2. And let's start with the simple case where the two off-diagonal elements of this metric are averaged to 0. And this is actually a pretty common case. So then in this case, we can simply replace this quantum metric by the Berry curvature, by the absolute value of the Berry curvature. And this is the geometrical bound on the dissipation rate. We call it geometrical because it has some geometrical interpretation, but we still have this non-universal parameter gamma inside the integral. So then to obtain a better bound, or to more interesting bound, we take this gamma parameter outside of the integral and replace it with its minimal value over the integration domain. So this function is always positive, so this is meaningful. And then we're left with the integral over the Berry curvature, and that gives rise to the topological bound, which is proportional to the absolute value of this Scherr number. And this is exactly the same Scherr number as in the frequency conversion. So the interpretation of this formula is that if the system has a finite frequency conversion, so if C is non-zero, then there would be a finite, there would be a minimal heating rate. And the other way around, if the frequency conversion is 0, so if the Scherr number is 0, we can always find a protocol where there would be no heating. And the simplest protocol is just don't drive the system at all, and you get 0 frequency conversion and 0 dissipation.
But you do have examples where the system is driven, C is 0, but you can actually accomplish a protocol that leads to no heating.
That leads to
no heating?
No heating?
Yeah.
When C is 0?
Yeah.
Well, you don't drive.
No.
Oh,
With the drive.
With the drive? Well, we find the bound. The bound is 0.
Right, I'm saying, can you saturate the bound?
When you drive?
Yes.
No, because once you no,
use upper bound.
no, you can't. But well, I guess more interesting case is when C is non-zero. But when C is 0, anyways your protocol doesn't do anything. So you are interested in protocols where C is non-zero.
Well, if there is a way where, like the one that's asking, that would be interesting, because you're pumping in and not heating, right? But
yeah, but
that would also very non-intuitive.
Yeah, I mean, if you bound and you're not heating, you're not doing any work for the
Yeah.
I mean, in principle, it is possible. You are driving the system, but all the energy goes. That doesn't enter.
No, wait, but I mean, in a closed, I mean, yeah, sure, if it's an open system, that can be achieved, but in a closed system, how do you do?
Yeah, I mean, if you have a non-interrupting system, for example, you
Of
drive
course,
with
of course, there's no open system, but like generic integrables,
You-
non-integrables.
you wouldn't be able.
Right, okay, good.
Okay, so here we try to verify this numerically. And here this is the dissipation rate as a function of m, and here m is a parameter that determines the topological phase of the pump. So when m is between -2 and 2, the system is topological, and when m is greater than 2 or lesser than -2, then the system is trivial. And here the brown area is the total dissipation. The bright area is the geometrical bound, and you can see that these two are very close to each other. And then the blue area is the topological bound. So let's start with the trivial case. So in the trivial case, the topological bound is 0, and the actual dissipation also approaches 0 in this limit. Well, it's never 0, but it will be as small as you wish if you take n large. Now, if we are in the topological phase, so here the topological bound is non-zero, but you can see that it is not very tight. And the main reason why it is not so tight is because we have variations in the gap, so we cannot find a good bound on this gamma function that we take outside of the integral. So then we use a different model where we fix the gap. And in this case, the topological bound is much better. Okay, so this was in the case when this off-diagonal element of the quantum metric was averaged to 0. If it is not true, then it is much harder to find a bound. And well, we worked hard and we found some kind of bound that depends on many different parameters. And what is interesting here is that this bound in principle can be lower than this topological bound that we found, and that gives rise to a possibility that we can find some protocol where the bound and where the actual heating rate would be lower than the topological bound. And we couldn't find such a protocol, but in principle, it might be possible. And then finally, we just for completeness, what would be the upper bound on the heating rate? So in principle, there is no upper bound because we can always drive the system back and forth and generate a lot of heat. And what we found is that the upper bound is proportional to the powers of the difference. Okay, and just, I guess, okay, good. So I'm about to finish. So how we can realize this topological frequency conversion? So there are several platforms where we can do that. So there is a platform where we can use magnetic spins, circuit QZ. There was recent suggestion to do it in superconducting qubits, and recently there were these two works. One that we did, that I was a part of it, where we explored the possibility of realizing this topological frequency conversion in materials, and there the spins are. So what plays the role of the spins is the pseudo spin in wildstone metals or in graphene. Okay, and let me just, by one slide, tell you what is next. So this is a project that we are working on now. So far we discussed this frequency conversion using this phenomenological model of this master equation, and now we are actually trying to simulate this problem in an actual many-body setting. And here we can. It turns out that we can represent this model just by two SYK dots, where the hopping between the dots is parameterized by this V of t, the magnetic field is a function of time. And we are currently in the process of doing this numerical analysis. Okay, so let me just summarize. So in this talk, I discussed the problem of heating, and we used two different approaches. So the first approach, we considered exact evolution using the SYK model. We showed that using this approach, we showed that a model of the total response with interactions can have quasi-steady states that exhibit high entropy density and yet robust topological response. And in the second part of my talk, I discussed the problem of heating using master equation. And this approach gave rise to some links between heating and quantum geometry, which can lead to topological lower bounds on the heating rate. Thank you.
Question?
But can you comment on like what it takes in generic models to come as close as possible to the bound?
Yeah. So essentially, okay, so this is sort of in the like we are working in the time domain, but it is similar to like the conditions for the bound to work. You basically want there are two things you need to have. So first of all, you have this gamma parameter that we approximate by gamma mean, right, by the minimal value. So basically, if the gap depends on time, the bound will not be perfect. So you want a system where the gap is constant as a function of time. And the second, you want the Berry curvature to be. So basically, it's the same condition as this vortex stability for materials. So if you can realize vortexible band as a function of time, right? So if you can realize the protocol to drive the magnetic field would change in time such that it corresponds to some vortexible band for the spin, that would saturate the bound.
Okay, then,
So this is not the Lokia band, it's
where's the definition of exact definition of gamma?
sorry. Gamma, in this case, gamma is this function, the simple function. It's like 1 over the tau in this regime, linear in this regime. It's some simple function in the prime. And you get it just from, if you explicitly calculate, it's not perfect.
Solve the, well,
Yeah, so you just solve this equation with this answer. You get this result.
Another question? Okay, speaker again.